Welcome to physics for February the 11th. So I'm speaking live to the A-Day class right now, but also the B-Day class. This is going to be my only interaction with you. So let me speak to the B-Day class for just a minute. Because of the weird schedule that Cottonwood did, that they set up, you guys got cheated out of a face-to-face class session. And but I think that's okay, because as long as I record this session and then you guys watch this session, you'll get what you need to get out of it. The agenda for today is we're going to go over homework 15C, which we didn't get a chance to do last time. And then we will, let's see, somebody just got here. Let me let her in real quick. Mark her tardy there. Okay. All right. So we're going to go over the answers to 15C. And then we're also going to go over the practice test, which I'm trusting that you guys did what I asked you to do. You got the messages that I sent to you. So I'm trusting that you downloaded the practice test and have worked on many of the problems there. I didn't expect that you did all of them, but I did want you to try them. And then as of this morning, I have now unlocked the answers to the practice test. So if you look on Canvas, they are available right now for you to look at. And then today, we obviously don't have time to go over all of them, but I think we can do the ones that are the most difficult. The ones that I know from past history are the ones that tend to give students the most problems. Okay, so now before we do that though, just a couple real quick announcements. The test is of course going to be next time we hold class. So if you're on the A-Day schedule, then for you, it'll be Monday, or not Monday, Monday's a holiday. It'll be Tuesday of next week. And then if those of you in the B-Day class, it'll be Wednesday of next week. Standard policies apply. All quizzes need to be retaken before we take the test. I will not accept any quiz retakes afterwards. Late homework needs to be turned in before we take the test. Now for quizzes, you can retake them without it costing you a late pass. Homework, on the other hand, if you turn in your homework late, that is going to cost you a late pass. A few of you have used up all of your late passes. I would still recommend you turn in the homework, even though you won't get credit for it. At least not, you won't get credit for the homework itself. The fact that you do the homework will greatly improve your odds of getting a good score in next week's test. Now, some of you, the pendulum lab reports that you submitted, you didn't get great scores on those. If you want to use up a late pass, I'm okay with you rewriting and resubmitting your pendulum lab report. Now that would be a good way to spend your late passes, because the lab report is worth a lot more than regular homework assignment is worth. So that would be a late pass well spent for many of you. Okay, now, so today we're going to go over a lot of questions, but you will probably still have some questions after this session is over that we just didn't have time to get to. So what do? Well, the tutors. Your first line of defense is the tutors. We have set up lots of opportunities for you to get tutoring help. Tuesdays, Thursdays, Fridays, Saturdays. Actually, on Saturdays, we have 2 different sessions on Saturday. So you have lots of opportunities. So go to the tutoring sessions, talk to them. If for some reason they're not able to satisfactorily answer your question, send me an email. I'll try to answer it via email. If for some reason email just isn't working and we're just not doing it for you, you're not able to understand what I write in my email response, let me know. We'll set up a live Zoom session sometime over the weekend. I will give up some of my weekend time to help you, and we'll set up a face-to-face Zoom session where we can talk live, and we'll get your questions answered. But please try the tutors first. That should be your first line of defense. Only come to me if the tutors are not able to answer your questions. With that being said, I think I'm ready to move on to the homework 15C. Do any of you have questions? Okay. All right. So I see that somebody is already submitting questions there. So Aubrey, I see what you're saying, and I will get to those. So she's asking about the practice test. we will do that. But before we do the practice test, I want to spend a few minutes talking about 15C. So, well, first off, let me show you the answers to 15C, at least the ones you haven't already looked up in the back of the book. Okay. So here are the answers that you haven't already seen. So for the next few minutes, restrict yourself to just 15C. So if you could only see one or two problems worked through from 15C, which ones would you want those to be? All right, so I'm seeing a vote for 86. Is that all? Find that hard to believe that's the only one you have trouble with. How about the rest of you? Come on, let's see some votes here. All right, 86 or 26. Okay. 26. Okay, so it looks like 86 and 26 are both getting kind of equal results. Last chance, going once, twice. Okay. All right, so we'll do both of those. We'll have enough time. Okay, so let me start with problem 26, and then we'll come back and then we'll do 86. So 26, resonance and closed pipes. Actually, 25 and 26 go together. Maybe let's talk about both of them. Okay, so 25 is resonance on a string, and 26 is resonance in a closed pipe. Let's just go over, let's group them all together. Strings, and then open pipe winds instruments and closed pipe winds instruments. Let's talk about all three of them together. So let me open up a whiteboard here. Right. When you have a stringed instrument, like you do in problem number 25, okay, if you look at what the string is doing, you'll see that it's fixed on each end, and then in between those fixed points is vibrating. So the simplest wave that you could possibly draw is the one that just has an antinode in between those two nodes. Okay. So it's fixed at each end. So that means you've got a node at each end. And that, I mean, that there's nothing you can do about that. You couldn't have it be an antinode if you tried. I mean, it's just by the nature of the way strings work, they're fixed at each end. So you have a node there. So on the simplest possible wave that you could draw there, what you'd have in the middle would just be an antinode. And so this would be the fundamental. But at the same time, you could have one of the harmonics resonate on that same string. So let me switch to red here, and let's draw what the next harmonic up would be. So the next harmonic up has to be fixed at each end. We have no choice about that. But in this case, we're going to have a node in the middle as well. Okay, so the wave is going to look like that. And then when it hits and reflects and bounces back, it's going to come back like that. So that's what the sounding wave is going to look like for the first harmonic. Okay, now let me switch to green. Oops, didn't want to do that. Oh, I hate it. And that means, okay, so my screen's doing weird things here. Let me stop sharing and go back into here. Okay, oh good, we didn't lose it. Okay, all right, so I'm going to switch to green here. So in green, we're going to have the second harmonic. Okay, and so that one again, you got a node at each end. Nothing you can about that. This time we're going to have two nodes in the middle. So that means our wave is going to look like that. And then it's going to reflect and come up like that. Okay, so all of those guys are going to be vibrating all together on the string. Okay, now, if we get rid of this third harmonic or the second harmonic here, just because, so my picture is not quite so cluttered. Okay, and now let's go back and let's redraw in that second harmonic, or I'm sorry, the first harmonic there. Okay, so you'll notice that the wavelength of the red wave is half the length of the blue wave. All right, so that means that the wavelength for the first harmonic is 1/2 the wavelength of the fundamental, okay? And so since the frequency equals V over F, whoops, sorry, let me try that again. Actually, the way I like to remember it is lambda equals v over f, and then I swap places with those. So f equals v over lambda. So if the first harmonic has lambda that is 1/2 of the fundamental, okay, that means that the frequency of the first harmonic is going to be twice the fundamental. So the frequency of the first harmonic is going to equal twice the frequency of the fundamental. And then the next harmonic up after that is going to be 3 times it, and then 4 times it. So all of the frequencies that are going to be vibrating on this string, you're going to have a fundamental, and then you're going to have the first harmonic, which is twice that. You're going to have the second harmonic, which is twice that, and then the next harmonic, which is 3 times the fundamental, and the next one after that is going to be 4 times the fundamental. So this is the pattern that is going to follow. So on problem number 25, if they tell you that the fundamental is 370, well, all you have to do is just take 2 times it, and then take 3 times it, and then take 4 times it, and bingo, there you go. Okay, that's a string instrument. Now, what if it's a wind instrument? Okay, so if it's a wind instrument, so there's 2 possibilities. It could be open on one end and open on the other. So here's the pipe that's open on both ends, okay? And then the other possibility is it could be open on one end, but it could be closed on the other end. All right, so if it's open, then the pressure there has to be room pressure. If you're blowing a trumpet, inside the pipes of the trumpet, you could have regions of very high pressure and very low pressure. But when you come to the end of the trumpet where it's open to the atmosphere, the pressure there has to be room pressure. There's no way, no matter how hard you blow that trumpet, you're not going to change the pressure of the room. It is what it is. So that means that wherever the wind instrument is open to the atmosphere, you're going to have a node there, whether you like it or not. Okay. All right. So if you look at what the wave that looks like that's vibrating inside there, you're going to have a node at each end, and you're going to have an antinode here. And you say, hey, wait a minute, that looks exactly like the string instrument. And so it's going to follow the same pattern that it does for the string instrument. So you're going to have a fundamental frequency, and the next harmonic after that is going to be twice whatever the fundamental frequency is. The next one after that is going to be 3 times whatever the fundamental frequency is, and so forth and so on. So it follows the same pattern. Now that frequency is V over lambda. V is going to be different for a wind instrument than it is for a string instrument. If it's a wind instrument, that V is always going to be 343, or whatever is the appropriate number, depending on what is the air temperature and the air pressure. But for most of the time in physics, we assume standard temperature pressure. Okay, so V is going to be 343 if it's a wind instrument, whereas if it's a string instrument, that the wave that's bouncing back and forth there is not traveling through air, it's traveling through a string. So V is going to be a different number for a string instrument. Okay, but the equation is the same equation, and the pattern that it follows is the same pattern for a string instrument as it is for a wind instrument, if the wind instrument is what we call an open pipe wind instrument, where it's open on both ends. But question number 20, whatever that is, 26, okay, I can't see without these guys. Question number 26 is not asking about an open pipe, it's asking about a closed pipe. Okay, so tell you what, let's just open up a new word here. So let's see what the pattern looks like here. So if it's a closed pipe instrument, and it would help if I could spell closed. Come on, let me erase here. There we go. Okay. Well, a closed pipe instrument is not closed on both sides. It has to be open on one side, otherwise you wouldn't get any music out. So it's closed on the bottom end, but it's actually open on the top. But we call it a closed pipe instrument. Okay, so wherever it's open, it's got to be a node. Wherever it's closed, it's going to be an antinode. So that changes things. So instead of having a node down here, I'm going to have an antinode down here. So if I were to draw the simplest possible wave, that is what it would look like. That is the fundamental wave, right? And so we look at that and we say, well, that if you started the node, so here's a generic wave, right? And so this from here to here would be one wavelength. So if you start at a node and you stop at the first antinode, how much of a wavelength have you gone? You've only gone 1/4 of a wavelength. So in this case, L is equal to 1/4 of the wavelength if we're talking about the fundamental wave. Okay. So then if you multiply both sides by 4, what you get then is that lambda equals 4L. And so when you take F equals V over lambda, you stick in 4L. And so you will find that the fundamental frequency that we get for this pipe is going to be a different frequency than it was back here with our open pipe. Let me get rid of a couple of things here. Okay. So even if this pipe that you see right here is the same length as the pipe that you see over on the right side, the fundamental frequency is going to be different because in this case, L equals lambda over 2. No, sorry. So this is the closed pipe. So in this case, lambda equals L, or L equals lambda over 4. Whereas in this case on the left here, L equals lambda over 2. So your fundamental frequency is going to be different, but also the pattern is going to be different. Instead of having the pattern being the fundamental and then twice it and then 3 times and then 4 times it, over here the pattern is you've got the fundamental and then the next harmonic up is not going to be 2 times the fundamental. It's going to be 3 times the fundamental. And then the next harmonic up after that is going to be 5 times the fundamental. And the next one after that is going to be 7 times the fundamental. Okay, so the pattern changes. And also the number that you get for the fundamental changes. Okay, so make sure you understand those. All right, so if you understand what I just said, then hopefully that will help you understand why we got the answer that we got for number 26. Okay, so are you good with 26 now? Can we move on, or do you want to actually do 26 all the way through to where we get the numbers? So type in the chat box, either say move on or say let's do it. Okay, so I'm seeing a lot of move on. So I do see a couple can we do it. Okay, it won't take very long. Let's do it. Even though most of you said move on, I did get a couple of you who in private messages asked me to do it. So yeah, let's just do it real quick. It shouldn't take too long. Okay, so the length of the pipe is 24 meters. We want to know the fundamental. Okay, well, let's go back here to our whiteboard. Okay, so let's open up a new one. So we just start from scratch. Okay, so 26 is a closed pipe. So it looks like this. So we got a node here and we've got an antinode here. So we know that L is equal to lambda over 4, which means that lambda is equal to 4L. And we know the frequency equals V over lambda, which in this case is V over 4L. And so since this is a wind instrument, we're going to assume standard temperature and pressure. If they don't tell you otherwise, you can assume that it's room temperature at sea level. So V is going to be 343. Now they might tell you otherwise, so be careful about that. But if they don't tell you otherwise, you can assume that. Okay, and then the length they tell you is 2.4 meters. All right, so where did my calculator go? Okay, so I get 343 divided by 4 and also divided by 2.4. Okay, so I get 35.7 hertz. Okay, so that is my fundamental frequency. That's 35.7, not 357. Okay, am I allowed 3 sig figs? Yep, I am. Okay, good. All right, and now on part B, they say that we've got a second pipe that is playing at the same time, same time. And this second pipe was supposed to be the same musical note as the first one, but the people who made the pipe messed up and they made the pipe a little bit too long. Okay. So when we play these two pipes together, the frequencies are going to be very similar, but not the same. So in a situation like that, we're going to have what we call a beat frequency. All right. And so they're saying that we're going to hear a beat frequency where the beat frequency is 1.4 hertz. Okay, so remember that beat frequency, that's that kind of a wah, wah, wah that you hear. And the rule for beat frequency is that whatever is the frequency of the beat that you're hearing, that is the frequency difference between the two things. So that tells us that the frequency of this guy right here is either 35.7 plus 1.4, or it might be 35.7 minus 1.4. Okay, it could be one or the other. All right. So which one is it? Well, if the tube is longer, that means that the frequency is going to be lower. So that means that it's this one right here. So that means that the frequency of that guy is going to be whatever 35.7 minus 1.4 is. So I'm thinking 34.3 hertz. That is the frequency of this guy right here. And so if we use this equation right here, we know that the frequency equals the speed of sound over 4L. So if we swap places with those guys, that means L is going to equal the frequency over 4 times, I'm sorry, it's the speed of sound divided by 4 times the frequency. So we just take this number and stick it in for the frequency, and the speed of sound is still 343. That doesn't change. All right. And so when you do those, when you stick those in and you do the arithmetic, you should get this answer right here. You should get that the length is 0.1 meters longer than the other tube. Okay. Now remember this number that we're seeing here. This is how much longer it is. That's not the length of the tube. That's how much longer it is than it's supposed to be. Okay. All right. So, and then the other one that you guys wanted to see was 86. So let's take a minute and do that. Okay. So on 86, what we got is we're dropping a rock into a well. So this is a great review problem. I love it because it takes some of the stuff that we learned a couple of months ago that some of you might have forgotten, and it makes you dust out the cobwebs from your mind and remember what it is. So we got a well here, and we're going to take a rock and we're going to drop the rock into the well. And so as it falls faster and faster and faster. And so the well is 122.5 meters deep. And we want to know how long it's going to take to before we hit the hear the sound. Okay, so this is a two-part problem. So part one, we ask ourselves how much time is it going to take for the rock to hit the bottom of the well. All right, so we say, gee, if only we knew an equation to handle accelerated motion. Well, pull out your Dr. Seuss equations. So XF equals X naught plus V naught T plus, that's a t, that may not look like it, but that's a t, plus 1/2 at squared. All right, so if we define our origin to be up at the top, so x naught equals 0, and notice they said we dropped the rock, we didn't throw the rock. So that means that v naught equals 0. So these guys go away. So what we're left with is x final equals 1/2 at squared. And so just solve for t. So if we multiply both sides by 2 and divide both sides by a and take the square root of both sides, so what we get is t equals the square root of 2 times x final, which is the depth of the well. So let me call it d, is the depth of the well, divided by a, which is, of course, really the acceleration due to gravity, which is g. Okay. So what we get then is the amount of time for the rock to hit the ground, or to hit the water in the bottom of the well there, is the square root of 2 times 122.5 divided by 9.8. And so I get, it takes exactly 5.00 seconds, a suspiciously round number. Sounds like they purposely manipulated this. Okay, but that doesn't mean that we're going to hear the sound 5 seconds later, because it takes time for the sound waves to travel back up to us. So this is just the time for part 1. We also need to know part 2. Okay, so part 2, we've got the sound. Now the sound is not accelerating, it's traveling its constant speed. So we can go ahead and use dirt, d equals r times t, which means t then equals d over r. Okay, and remember, this is not the total time. This is, I'm just going to call this t2. All right, so we know what the distance is, and what about the rate? Well, do we use standard temperature, pressure, or whatnot? So do they tell us anything about the temperature inside here? They don't. Okay, so we're going to have to assume that it's just standard temperature and pressure. So that means the speed of sound is going to be 343. Okay, so that means that we're going to get 122.5 divided by 343. So that means that it takes 0.357 seconds for the sound to come up. So what's the total? Well, the total is going to be that plus that, add them together, and that will tell you what is the total time that it'll take before you hear the sound. Okay, so that's where we get 5.36 from. Okay, now 27 and 29 I wanted to discuss. So let's just take a little bit of time to talk about those. 27 was asking, let's see, what was that? Okay. 27 is asking about timbre. And so basically, I just wanted to make sure that you guys understand, why is it that if you listen to two musical instruments, let's say one's a violin and one's a flute, they're both playing the same note, and yet you can tell the difference. You can tell which one's the violin and which one's the flute, even though they're both playing the same note. So we talked about this last time, but I just want to take a minute here to make sure you fully understand it. Okay, so when you play any musical instrument, okay, the wave that you get is not going to be a pure sine wave, although it's made up of your sine waves. So what's going to happen is you're going to have a fundamental frequency vibrating that's going to look like that. At the same time, you're going to have the first harmonic going, which is going to be like that. Now, the amplitude of this and the amplitude of that are going to be, very different. It depends on what kind of musical instrument it is. And at the same time, you're probably also going to have the next harmonic up after that. So it's going to be like this. Okay, so the things that make up what you hear are sine waves. But when you add these guys together, the resultant wave that's the sum of all these guys, that does not look like a sine wave. That's a wave that looks something like this. Okay, it's a periodic wave, but it is most definitely not a sine wave. Even though its constituent parts are sine waves, the sum total of those parts is a wave that is not a sine wave. And the shape of this wave is going to be different depending on what musical instruments it is, because when you mix in the different frequencies, they're going to mix in differently. With a violin, maybe the amplitude of your fundamental is stronger and the amplitude of these harmonics is weaker. Whereas with the flute, you know, maybe it's the other way around. Maybe the amplitude of this harmonic is stronger than the others. You know, so remember when we played around with this on Desmos, by playing with the amplitudes of the different harmonic frequencies, we can get a wave that looks very, very different. But the period of the wave, which determines the frequency. So the period of the wave is going to be the same, but the shape of the wave is going to be different. So I just wanted to make sure that you understood that. And so number 29 is kind of an interesting one. Okay. So for number 29, okay, I've got a tuning fork. Okay, so if I take my tuning fork and I hit it with a hammer, now I can hear it. Can you? Maybe very, very, very faintly, but probably not. Okay. But I can hear it. Okay. So if this was a musical instrument and I'm playing this musical instrument, but my audience can't hear the musical instrument, that's not very good. My audience is not going to be happy. I need to have some way of magnifying the sound. So what I get is I get a sound box, basically just any large you know, sheet of wood or music or whatever. So then when I hit the instrument, and so what I'm going to do is I'm going to walk this on my knee and I'm going to hold it up and then I'm going to touch it so it's touching the sound box and then not. So let's see if we can tell the difference. Do you hear that? When I take it away, it goes softer. When I touch it, it gets louder. Okay. No touching, touching. Could you hear the difference? Okay. So what's happening is that the vibrating tuning fork is setting up vibrations in whatever it's touching, and because the sound box has more surface area, when it goes forward and back, it can move more air, which means that my audience is going to be able to hear me. But at the same time that it increases the amplitude, it also mixes in some harmonics that weren't there before, because the box is not only going to vibrate at the fundamental frequency, but it's also going to vibrate at some of the harmonics as well. And so not only do I amplify the sound, but I change the timbre. I change the flavor, the sound quality. It's still the same note, but it sounds different now because I've mixed in some harmonics. Okay, so I think that's good for homework 15C. Let's go ahead and let's move on to the practice test. Now, I would hope that you guys have already downloaded the answers to the practice test. Here they are. Okay. In fact, tell you what, it's a little bit hard to see there. Let me open it up in a different way that makes it a little easier to see. Okay, let's open it up here. Okay, and then let's move up to the top. Okay, so remember the way that I used to do my tests and my practice tests back before coronavirus was I always gave them in two parts. Part one, students were not allowed to use a calculator or a cheat sheet. Now for you guys, you will only have one part to your test and you will be able to use a calculator and a cheat sheet, and more than just a cheat sheet, you'll be able to use all of your notes and even the book and even the internet if you want. But if you take time looking through the book or flipping through the internet, you are going to use up precious time and you're probably going to run out of time before the test is over. So I strongly, strongly, strongly recommend you make up a one-page cheat sheet before the test. Have all the important information on that one-page cheat sheet so you don't have to waste time flipping through it. Now, that being said, there are some things that I do believe that every physics student should know without needing to look on a cheat sheet. And so all of the questions that you see here on part one of the practice test, those are the kind of things that I really, really wish you would learn well enough that you would know it without needing to look on a cheat sheet. So if you haven't already done all of these problems on the practice test, when you do the parts on part one of the test, when you do the problems on part one, please try to do it without a cheat sheet. Okay. I mean, if you have to, okay, do it, but try it without. Okay, so the first couple of problems are what I hope are basically really simple ones. If the car is driving away from you, you're going to hear a lower frequency. I mean, you guys know that from your everyday experience. Number two here, as you play with the amplitude of the vibrations, how does that affect the wavelength? Well, remember that online simulator that we played with? I want you to go back and play with it. I put a lot of really, really good online simulations into Canvas for you. Play with those things. Play with the amplitude, and you'll see that you can change the amplitude all you want. That doesn't affect the wavelength. You can change the amplitude all you want. It doesn't change the speed of the wave. Okay, but if you change the frequency of those things, okay, then yeah. So the frequency that will affect the well, I'm sorry. I'm a little off here. Let me try to bring, okay. So the frequency, that will change the wavelength, okay? But the frequency doesn't change the speed of the wave, because the speed of the wave only depends on the properties of the medium. So that means it depends on how thick the string is, and it depends on how tightly the string is stretched, but it does not depend on the frequency or the amplitude that you're vibrating with. Okay, so changing to heavier string, yep, that's going to change the speed. Changing the tension of the string, yep, that's going to affect it. Okay, so play with those online simulators, please. You will find those are great things. Okay, the next couple of questions, those are all basically just definitions. So you should be good on those, I trust. Question number 5 is just, can you read a graph? And can you identify, what is the amplitude, what's the wavelength or the period, depending on what the independent variable is. So that one should be easy. Question number 6 is deriving our new favorite equation. I definitely recommend that you know how to derive that. It's very, very simple. And deriving equations is what I think makes physics physics. Question number 7 is Hooke's law. I would hope that you guys agree that's pretty straightforward. Question number 8 is just make sure you know how frequency and period are related. Question number 9, you just need to know the equation for if you stretch a spring, then how much force does it take to do it? Okay. And so Hooke's law is what you're going to use for that. All right, question number 10 maybe is worth taking a little bit of time to talk about. This is one that I know from experience people sometimes have a little trouble with, because I'll admit that it is a little confusing, because when I ask how much louder is one wave than another, well, it depends on how you define loudness. So let's open up a whiteboard and just talk about how I recommend that we do this. Okay, so what I recommend is draw a scale that looks something like this, where each tick mark is a 10 decibel increase. So if we start at some number, like let's say we start at 40 decibels. So then every tick mark above that is 10 decibels more. So there's 50, 60, 70, 80. Pretend like they're evenly spaced. I obviously didn't make them very well evenly spaced, but pretend that they are, okay? All right, so when we talk about loudness, there's 3 ways we could do it. We could be talking about the power that is delivered by the wave, because remember that a wave carries energy. And so power is how much energy divided by how much time. So in black ink, I'm going to talk about the power. In red ink, I'm going to talk about the amplitude. Okay, so remember, if you have a wave that looks like this, okay, so that's the amplitude. It turns out that the power is proportional to the amplitude squared. Okay, so remember that relationship. And then in blue ink here, we'll talk about the perceived loudness. Okay, so those are the three ways that we could define loudness. So when I ask you how much louder is a wave, your first reaction should be, well, which of the three ways do you want me to refer to it in? Okay, so let's go back to black ink here. So let's talk about power. So power is the way the decibels were originally defined. So if you go up from anytime you go up by 10 decibels, that would be a 10x increase in the power. So when I go from 40 to 50, that's 10x. 50 to 60, that's another 10x. Okay. 60 to 70 is another 10x. 70 to 80 is another 10x. So if I go directly from 40 to 80, okay, that is not 40 times. That's 10 times 10 times 10 times 10. So that is 10,000. That's a 1 with 4 zeros. Okay, so the power, so if I'm going from 40 to 80, that would be a 10,000 time increase in the power. Now, what if I'm interested in the amplitude? Okay, so the amplitude is the square root of the power. So with amplitude, if I go up a 10 decibel increase, that is an increase of the square root of 10 in terms of amplitude. Okay, so if I go, so here's the square root of 10, here's another square root of 10. So that means from here to here then is 10. And then again, here's another square root of 10, another square root of 10. So from here to here is 10. So what that means is if I go directly from 40 to 80, and amplitude is what I'm worried about, it's 10 times 10. So it's 100x increase in amplitude. But I might be talking about perceived loudness. Okay, so the rule with perceived loudness, here, let me get this out of the way here. With perceived loudness, if I go up 10 decibels, that is approximately a 2x increase. Now I have to say approximate because it's not exact. With power and amplitude, it is exact. But for perceived loudness, it's just approximately half, or approximately 2. So if I go from 40 to 80, so that's 2x plus times 2x is 4, times another 2 is 8, times another 2 is 16. So that would be a 16x increase in perceived loudness. Okay. So if I go from 40 to 80, these are the results. Now in the practice test, I didn't go from 40 to 80. I went from 50 to 90, but that's going to be the same because the number of steps from 50 to 90 is the same as the number of steps from 40 to 80. Okay, so the answers that we got before are the right answers. So make sure you guys understand that. I'm not going to make you do the equation that has the logarithm in it. I just want you to understand what we just talked about there. Okay, question number 11 is the one that we just got through talking about. Why do flute and violin sound different even though they're both playing the same note? So we just got through talking about that. So I'll just skip over to here. Okay, now here's the fun part. This is part 2 of the test. This is the part where you're going to need to use a calculator and you're probably going to want your cheat sheet. The things that you see on the screen right now, these are things that I will include up at the top of the test. So you don't need to waste time looking up what is the speed of sound in various media here. You don't have to worry about that because I will give that to you. So basically everything that you see right here, all of these equations, this table, everything you see there, I will put this up at the top of the test. So hopefully, it'll be helpful to you. Okay. All right. So now we have a bunch of problems here that we need to go through. Before I do that, let me ask for your input. Can you guys please vote? So of the problems that you see in part number 2 of the practice test, if you could only see one problem worked through, what would you want that one to be? Type it into the chat box. And you can do it privately if you don't want anybody else to see it. That works fine. Okay, so I'm seeing 21. I'm seeing somebody say any of the last 6. But how about like 12 through 20? Okay, so 16. Somebody's voting for 16 there. 12, 15, any of the last few. Basically any of them. Okay, so I'm not seeing a great consensus there. All right, so tell you what I'm going to do. I'll go through them and I'll try to get all of the important ones. Okay, so question number 12. This one's just a graph reading one, so I hope that you guys will be able to do it. Now, the quality of my graph here, oh my goodness, this is horrible quality. Yuck. So on the real test, I will not, I mean, this is a photocopy of a photocopy. The numbers are there. I mean, if you look, you can see the numbers, but it's really hard to tell. So if you can make out this horrible graph here, you'll see that the nodes appear right here. So 0, obviously. Okay, so this node right here, because of the horrible quality of the reproduction, it's hard to tell. But if you could read the graph, you'd tell we've got a node right here, which is about 2.8. We got another node right here, which is about 5.8. Okay, and then obviously we have a node at the end, the antinodes. So this one is basically just, can you read the graph? Which, if it was a better image quality, you should be able to do easily. I apologize for the really poor image quality on this one. Okay, so number 12 should be fine. I'm hoping that we don't have to worry about that one. Number 13 is basically just, do you know how to use the equation here for this equation right here? So there's a lot of different ways that I could do this equation. You know, I could tell you what L is, and I could tell you what G is, and I could ask you to calculate T. Or I could tell you what T is and ask you, and tell you what L is and ask you to calculate G. Or, you know, whatever. Any of these three variables, if I give you any two of them, you should be able to calculate what the third one is. So just make sure you know that equation. Okay. Number 14, well, that's just everybody's new favorite equation here. So lambda equals V over F, right? So if I tell you what any two of those are, you should be able to calculate the third one. And so you should recognize that if it's seawater, you know that the speed is this, but be careful because it might not be seawater, it might be fresh water. So then the speed will be different. So just make sure you're very careful about reading the question and looking to see what is the medium that we're talking about. And also what is the temperature, because the temperature affects things as well. So anything that I give you on the test will be one of these guys that you see on this table right here. Okay, I'll restrict it to only these. Number 15 is a good one. I think that was one that several of you asked about. And so I think it's probably a good idea to spend a little more time on this one. Okay. So what I tried to illustrate here is that we've got a spring where right here the spring is squeezed, the spring is compressed. Okay, and so there's energy stored in that spring. So you guys should know that whenever you have a stretched spring or a compressed spring, the energy that's stored in there is 1/2 kx squared, where x is how much has it been squeezed, and k is the spring constant of the spring. So, and now rather than just calling it E, let me call it SPE, where that stands for spring potential energy, right? So if you look at the before picture, you'll notice that the car is not moving. So that means the kinetic energy equals 0. And it's at ground level. So that means gravitational potential energy is 0. So if we say, how much energy do we have before? Well, all we have is spring potential energy. There's nothing else. Okay. Now, what about the after case? Okay. So the spring has sprung. So it now has 0 energy because it has given all of its energy to the cart. It's no longer compressed, so we no longer have any energy stored there. all of the energy that used to be in the spring has now gone into the car. And so if it's moving energy, then it's kinetic energy. So 1/2 kex squared before it sprung must equal 1/2 mv squared after it's sprung. And from this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? So just take that, solve for v, stick in the numbers, and bingo, out pops your answer. So this, I would hope, is an easy problem. Just make sure you understand what's going on here. So we're storing energy in the spring, and then we give that energy to the car. Okay, Doppler equations, make sure you guys are really good about Doppler equations. The thing that people mess up on is the pluses and minuses for the source and the detector. So I highly recommend that you draw a picture. Just even if you don't think you need it, draw it anyway. So for part A, here's the car. Okay, the car is moving that direction. The detector is the person standing right here, and that person is not moving. So if the speed of the car is 21 meters per second, does that mean that v is a positive 21, or does that mean that v is a negative 21? It's going to be one of those two. How do you know which one it is? Well, what's the plus direction? Okay, so I want to take a minute. I want you guys to type in the chat box in a private message. I want you to say either right or left. So if you think that the plus direction is to the right, say right. If you think that the plus direction is to the left, say left. So I want everybody to type it in here and do it in a private message so other people can't see what you wrote. Okay, I'm not seeing very many answers here. What about the rest of you guys? Okay, it's looking better now. I'm still missing a few, but those, okay, so it looks like everybody has agreed the plus direction is the right. Now, how do we know that? What's the rule for defining the plus direction? What you do is you draw a line from the source to the detector, and that by definition is the plus direction. So if the car is moving the same direction, that means that the velocity goes in as a positive 21, not a negative 21. And now when we stick it into the equation here, you'll say, hey, wait a minute, Mr. Hendricks, there's a minus. I thought you told me that we put it in as a positive. Well, the equation says V minus VS. So if VS is a positive 21, so V minus a positive 21 is going to be 343 minus. Okay. Now, in part B, that's where things change. Okay. So in part B, the detector is not in front of the car. In part B, the detector is behind the car. So we're in another car following behind it. Now this car is moving the same direction, and how it's moving at 13, okay? But is that going to be a plus 13 or a minus 13? All right, well, what is the plus direction now? The way you answer it is you draw a line from the source to the detector. Notice this time the plus direction is to the left, okay? So that means this time in part B here, the velocity of the car is not 21 anymore. In part B here, the velocity of the car is negative 21 because our plus direction is now different than it was before. And then the detector so it's going to be a negative 13 because the car is moving to the right and the plus direction is to the left. So that means over here, we've got to enter our numbers like this. So it's going to be V minus a negative 13. And then on the bottom part, it's going to be V minus a negative 21. Okay, so minus minus is plus, so you get 511, which rounds off to 510. So every year, no matter how much I emphasize this about being very, very careful with your plus directions here, every year, people still get the question wrong on the test. And when I go to look at what they did wrong, they got their pluses and minuses wrong. So let's let this be the year where everybody gets it right this year. That would be so cool if everybody got it right this year. Okay, number 17, we've talked about at length a few minutes ago. So I'm not going to take the time to talk about 17 now. I mean, this is exactly identical to what we talked about at the very beginning of the period. Okay, actually, okay, maybe I will take just a few minutes or even seconds. So, okay, so if we have a pipe that's open at the top and closed at the bottom, that means we've got a node at the top and an end node at the bottom. So that means these are the equations that we use. Okay, and so this will tell us the fundamental frequency. This will tell us the first harmonic up after that. Okay, so what we talked about before. Now on question number 18, it looks like exactly the same question, but there's one extremely important difference. This one is open both at the top and at the bottom. Okay, so that means we're not going to have a node. Well, we are going to have a node at the top, but we're not going to have an end node at the bottom. This time we're going to have a node at both ends. Okay, so this equation, actually, tell you what, let's compare them. Let me come down just a little bit here. Okay, so there. All right, I think that'll work. Okay, so you'll see that if we look at the fundamental, so let's look at part A. Okay, so this equation and this equation are the same, but up here with our closed pipe, lambda was 4L, where down here with our open pipe, lambda is 2L. So even though the length of the pipe is the same, we're going to get a different fundamental frequency because at the bottom is a node rather than an antinode. Okay, and then our first harmonic up. Okay, it's going, if it's an open pipe, it follows this relationship, but if it's a closed pipe, it follows this relationship. So you'll notice this time around, the first harmonic is twice the fundamental, but if you look up here, you'll notice that the first harmonic is 3 times the fundamental. So be very careful about those. And if you're careful, I think you'll be good. Number 19. Now this is a good one. I like number 19. Let's take a little bit of time. How are we doing for time? Yeah, we're good. We'll be fine. Okay, number 19. A piano tuner. So have any of you, well, I don't know, I don't know if you guys even own a piano, but if you own a piano, have you ever had the piano tuned, and have you ever watched while the piano tuner goes to work? I know that there are lots of people who think that, I have perfect pitch. I can tell my ears are so good that if you play the piano and it's out of tune, just by me hearing it, I will know that it's out of tune. Well, that's baloney. Nobody has perfect pitch. Even people who work as piano tuners, they're not able to do their job because they have perfect pitch. They're able to do their job because they understand beat frequencies. Okay, so what they do is they get a tuning fork that is calibrated exactly for the note that they are trying to tune it for. Okay, and then they hit that and they listen to the tuning fork at the same time that they're playing that note on the piano. So what you've got is you've got 2 different frequencies that they shouldn't be different. I mean, ideally they would be the exact same frequency, but the piano's a little bit out of tune, right? So the piano is going to be a slightly different frequency than the tuning fork. So what do you have when you have 2 frequencies that are really close but not the same? You get that beat frequency. You get that wah, wah, wah type sound that we heard the other day. And by the way, it wouldn't be a bad idea to go back and play with that again. I put that link on Canvas. Go back to that online simulator for the beat frequencies and just play with it. Spend some time playing with it. It'll be time well spent. Okay, so in problem number, whatever this is, problem number 19. So the piano tuner is playing the note on the piano, and she's also got this tuning fork. And so the frequency is supposed to be 262. So the tuning fork is 264, but the piano is a little bit off. Okay, so they're hearing that wah, wah, wah. And so the time between the throbs is 1/2 of a second. Now, is that the frequency or is that the period? So this is what throws a lot of people off. When I word it the way that I did, I say the time between the throbs is 1/2 of a second. I'm not telling you what the frequency of the throbs are. I'm telling you what the period of the throbs are. And if you're dealing with beat frequencies, you need to know what the frequency is. All right, so you need to know that the period, whoops, hang on a second, because the period is 1 over the frequency, right? Or in other words, the frequency is 1 over the period. So if I tell you that the period is 1/2 of a second, then you should know, okay, well, that means that the frequency is 2 hertz. So what that means is that the piano is 2 hertz off from what it really should be. Okay, now that you don't know what direction it's off. It might be 2 hertz too high, but it also might be 2 hertz too low. So without additional information, you don't know whether the frequency of the piano is 264 or whether it's 260. You just know that it's 2 hertz off from 262. Okay. Now in part B, that's where I give you the additional information. Okay. So in part B, I'm telling you that when the piano tuner tightens the piano string, the beat phenomenon goes away. So once the beat phenomenon goes away, then the piano tuner knows that the piano is at the right frequency. Okay, so those of you that have played instruments, those of you that played string instruments, guitar or violin or whatever, when you tighten up the string, does that increase the pitch or does that decrease the pitch? Somebody tell me. And we must have some musical instrument players here. Any guitar players or violin players here? Okay, so Dylan is telling, and Calvin agrees. Yeah, so when you tighten up the string, that increases the frequency. So when we tighten it, if the frequency goes away, that means that the frequency we started off with must have been lower, not higher. So you see how this works? So I hope you guys agree this is not really all that difficult. I mean, most people tell me that the mathematics in the second half of the year, the mathematics that we use is easier than the mathematics that we used in the first half of the year. And I agree. I do think it's easier. That doesn't mean we're not using math. It just means the math we're using is easier. Okay, question number 20. You just need to recognize what does it mean when we talk about an octave. And so you need to know that if you got 2 musical notes and one of them is an octave higher, that means that the frequency is twice what the lower frequency is. Okay. And so if it's 2 octaves higher, okay, then it's going to be 2 times 2. So it's going to be 4 times. If it's 3 octaves higher, that doesn't mean that it's 6. It's not 2 plus 2 plus 2. It's 2 times 2 times 2. So if it's 3 octaves higher, that means the frequency is 8 times more. Okay, number 21. This is my favorite one on the test. And it looks like we have enough time to just barely do it. So I think we're going to be okay. So you need to recognize, well, first part A is, I hope you guys agree part A is straightforward, right? If you know how much time it takes for the pulse to go to the sub and back, I mean, you should have no trouble with that. Hopefully just use distance equals rate times time. But don't forget that that's the distance that the sound traveled, which is twice the distance that I want. So don't forget to divide by 2. Okay, so as long as you do that, I hope you agree that part A is really easy. Part B, that's the fun one. Okay, so what you need to do is you need to recognize that this is a 2-part problem. So if this is the ship and this is the sub, okay? So part one is the wave traveling from the ship to the sub. So the ship is the source. The sub is the detector. At least for part one it is. Okay, so part one, just use this equation. Be really careful about your pluses and minuses. Don't make mistakes there. And so what you'll get for part A, or you get what you'll get as an answer for part one is that the people in the sub will hear a frequency of 560.4. Now, what about part two? So let me switch to a different color here. So for part two, this is the return trip. So now the sound is traveling from left to right. So this is part two. So the sub is now the source, and the ship is now the detector. So be really careful about that. Okay. And also be careful about your plus and minus signs, because in part one, the plus direction was to the left. In part two, the plus direction is to the right. Okay. So notice that this speed right here, let me go to here. So this speed right here, this was the detector for part one, but now it's the source for part two. And it was negative in part one and it's positive in part two. And then same thing with this one. It was the source in part one. It's the detector in part two, and the plus and minus signs changed. So just be super careful about this one. Make sure you keep track of your plus and minus signs. Oh, and then the other thing to remember, the other thing that may not be obvious, this frequency, which is the frequency that the people in the sub hear, that becomes the source frequency for the return trip. That's something that may not be obvious. But if you think about it, I hope you agree that it makes sense. Okay, so just be super careful, and when you're done, you should get this answer right here. And then this is the number that will appear on your calculator, but you'll have to round it off to this. Okay. Okay. And then question number 22. This is where we derive the Doppler equation. Now, some of you are going to say, wait a minute, Mr. Hendricks, you never derived the Doppler equation. Okay, well, I didn't derive it, but I did give you a link in Canvas to a YouTube video where they derived it on the YouTube video. And I think they did a good job. I think they were clear and easy to understand. So I am going to hold you guys responsible for knowing that. You should be prepared that you might possibly have a question on the test that deals with deriving the Doppler equation. So spend some time doing that. Okay, well, that's it. We've got about 8 minutes left. If you guys don't have any questions, I'm okay with you typing by into the chat box and heading out. If you do have a question, but you didn't want to ask because you knew this was being recorded, let me go ahead and stop the recording so then you can ask your question without embarrassment.